So in the next hour of this talk, we'll get to a few more videos, and that gets a little more actually hands-on technical, or hands-on demo technical, if you like. But sort of the next level that I want to talk about here is platform as a service. And I mentioned Salesforce.com. They're kind of one of the really big players in this. And we had a little bit of experience with them through sort of an indirect relationship. And so we thought we'd have a look at them. And their selling point is that they say no more software. So they want to host your CRM, which was their original business model, but actually they also provide you with the ability to write applications. So they're both software as a service and platform as a service. And we had before getting into the platform stuff, we had a look at the actual application that they provided to you for CRM. And we tested it, and they had good filtering, and it held up, and it was fairly cursory. But what's interesting is that ultimately, of course, like all of these things, it's a web application, okay? Which means that web application security is still a changing world. We're still developing new attacks. And so we try to find a whole bunch of these attacks. And so this is one example of things that you may see on Salesforce.com. So you may be aware of Jeremiah Grossman's Clickjacking attack. And pretty much all this video demos is that actually Salesforce.com is vulnerable to clickjacking. Now, we can talk about how risky an attack clickjacking is, and there's while the worst case scenario is pretty bad, generally it's, the impact is less so. But I'll show you what the attack is. Pretty much, we're demonstrating here how to use a portion of the interface, and that portion of the interface talks about contacts and calendar events, and so on. And so this shows you how one might go about deleting an event. And so we click around the interface, and ultimately we're going to delete it. But the nature of a clickjack attack is that you get a user who comes to your evil page. I'm not sure if you can probably see just in the background, you probably just see like a watermark. And actually that watermark is the Salesforce.com website, but it's been positioned so that it's transparent, or virtually transparent in this case, so you can see what's going on. And the idea is that you're going to get the user to click on points on the screen where actually he's clicking on Salesforce.com, but he can't see Salesforce.com. He doesn't know he's clicking on Salesforce.com. Okay, so it's a UI redressing attack is the more formal name. But otherwise, it's also known as clickjacking. And of course, the way that you would get someone to click around an interface varies. I mean, you have a punch the monkey little game, or the dancing pigs, or whatever. But just you need a guy to click. What's interesting as well, of course, is that with clickjacking, it's developed to the point where you can position that background, or you can position the transparent page whenever the guy clicks. So actually, he just needs to click, and you'll reposition the page. Doesn't matter where he clicks. So you can get him to click around. And then with that clicking, actually those clicks get passed to Salesforce.com without him knowing, and of course this implements changes on the Salesforce.com website without him knowing. And why this is interesting, or why clickjacking is interesting, is that, or in the original example, they showed how you could remotely enable your microphone and video camera through clickjacking without knowing that you had done so. So there were, scary privacy kind of things happening there. But the point here is that Salesforce.com is vulnerable to an attack that's relatively well known, or it's really well known, and it's something that they've chosen not to address, which by extension means that your customer relationship management software is clickjackable because you're relying on Salesforce. But let's look a little bit more into actually what Salesforce.com provide their customers. So it's a 10-year-old company at this point, so they've been around the block. They started off doing CRM, but they've moved now. quite rapidly. They're a big company, over $1 billion in revenue. They've got almost 60,000 customers. They're a major player, and they've got some of their customers really are major players. Originally, they had this system which did CRM in the cloud, so it was software as a service. But increasingly, what they are marketing at, or what they are pushing, is their Force.com platform, which is the runtime environment that allows you to write your application within a custom code and run it on their systems. It's an ambitious project. They've got solid aims, and actually their heart is in the right place if you speak to them in terms of securing their systems. They're quite proactive with this whole thingam. Now, if we try to relate this back to some of the characteristics that NIST defined for cloud services, the big one here is that it's multi-tenant. There's resource pooling. The reason it costs you so little to run your services there is because you're sharing processor space, or you're sharing processor time, you're sharing storage space, you're sharing network bandwidth with a bunch of other people who probably don't all use the system at precisely the same time, so you can spread it out a little bit, and it costs everyone a little bit less. So it's quite cool. And it's a subscription model. So you pay to use it. The more you pay, the more you can use. The features scale with the more you pay. Okay, so it really does, it fits those characteristics quite well. But what's interesting for the purposes of our testing is that they gave us they hand out free accounts to developers. So if you're looking to write applications on Force.com, you can sign up for free today, right now, while we're sitting here. And it's quite a useful thing to play with. Of course, those accounts are a little bit more limited than if you paid, but you still get access to a lot of cool features. They also have their idea of an app exchange, in which is similar to the App Store that Apple has. So you can write applications for Force.com and put them inside of the app exchange, and you can sell them to other users. So you'll get things like an entire accounting package written for Force.com, which ties into the CRM system and all of this. But again, all access through a single web interface. So when we spoke about cloud being insidious, this is the kind of thing we're talking about. As it slowly grows, the features that become available and that may increase your risk profile are added without you particularly being aware of them. Now, in this case, you get to choose whether or not you use any of those apps. But if you do choose to do that, then you would need to reconsider your risk. And so if you look at how one might write applications within or on Force.com, so there's sort of three basic components. On the one hand, you can write the interface through a language called Visual Force, which allows you to specify all the cool things on how your HTML elements fit together and so on. Okay? But it's basically a templating language that sits in the front end. That's an example of how Force, or a Visual Force page might look. And you can see it's XML based, blah, blah, blah. But the more interesting stuff for me is when you actually get into the guts of the application and want to write the stuff that sits behind the interface. And there you get to Apex, and this is an example of Apex. It's a Java-like language. Their runtime environment is based, or their runtime environment is written in Java. And so they've got this Java-like language that gets executed within on the Force.com platform. And you can see there that it's what you'd expect any Turing complete language to look like. But the last part of that then is the data store. So they provide you with two interfaces to actually storing data. There's no such thing as a file. There's just a database, and you interact with that. And it's quite an interesting way that they've got it done. They tie, or the object relational mapping is built into the language. So you don't have external libraries to do that stuff. Objects are first order or first class types. And so you get SOQL and SOZL, so the query language and the search language, which basically allow you to do this kind of SQL-like query and immediately grab all the results of that SQL-like query into a list of objects and so on. So it's quite a full-featured language. It's quite nice for this stuff. The development environment is generally in your browser, so they have got a browser-based dev environment, which is also quite cool, or you can write in Eclipse with a plugin. So this is just an example of the browser-based dev environment. Now, the language has got a whole bunch of these features that allow it to live on the web, it allows it to live within the cloud. So for one, it can, from within your code, you can make an HTTP callout, you can request things. But of course, they need to be very careful about how people use these features. They are cognizant of the fact that just opening up all sorts of new APIs to people also broadens the scope for compromise or for bad stuff. So you can make HTTP requests, but in order to make an HTTP request to a given website, you need to first configure that through an administration interface and say, we explicitly permit our application to talk outwards to that site. It's also possible to have a web service endpoint sitting within force.com that when it gets called, your Apex executes in response to that. So you can have your code execute within the cloud in response to a web service call. You can also send emails, or you can have Apex execute in response to receiving an email. There's also triggers and so on. And when we were looking at this system, it kind of struck us that multi-tenancy is cool for reducing costs, but there is a problem there, and you're sharing space with other people. And sharing space with other people is uncomfortable, especially when you're dealing with private data and so on. And so there's things like, what happens if one of these guys, when he sleeps, rolls over and kicks me in the back? And, it's painful things. And you would see the same on a shared system. So you would want there to be equitable sharing of resources. One guy shouldn't be able to, or one application should not be able to steal all of the processor time, or one application shouldn't be able to take all of the storage, and so on. And so in order to separate applications, Force.com has got what they call governor limits. And governor limits are just quotas or restrictions that are enforced on your code. And so every time a script executes, it is subject to these limits. And some of the limits, well, we'll talk about some of the limits shortly, but when a limit is exceeded, pretty much your application is killed. At that point, an exception is thrown, and you can't catch it, and so it dies. The limits have got, well, they vary depending on how much you pay, depending on where the code is called from, and so on. But basically, every time code executes, it's got limits. And the limits, of course, vary if you purchase apps and so on. But some of the things that are limited, so for example, basic ones, the number of lines of script that can be executed in a given invocation of code. So depending on your account and what you've signed up for, that may be 200,000 statements will be executed in a given invocation. Or it may be things like the total size of code in a given class, or the amount of data that you've stored. Typically, it's about 30 megs of data you're allowed. You'll also have maximum limits on number of web requests, number of sent emails, and so on. But we also, through the testing, you bump into a number of unpublished limits. So they're playing it quite well in the sense that they're quite upfront about all the things that you're not allowed to do that would fit within the normal parameters for code that you may write. But they've also got a whole bunch of other limits that they're also checking that are indicative of malicious code that are not necessarily published. Okay. So they're being quite transparent with you where you are being transparent with them. So where you're writing code that is non-malicious, they'll tell you exactly where your code will die. But when you start to write code that pushes the boundaries, then you'll run into limits that they're not so open about. And things like that are going to be the length of time that a script can run, the number of emails you can receive, and I'd guess there are more. Those just happen to be the ones that we ran into. But this language does have some limitations, given that it's quite specific. So it's a domain-specific language. In this case, we've got it's focused on these short bursts of execution. And there's other minor painfulnesses, where you can't alter the configuration of your Salesforce.com account from within Apex. You can only do it through the web application and so on. If you can get your Apex code to talk to its own management interface through web callouts, well, then you can kind of step around that. But there's no explicit way to do that. There's also no explicit locks in the code. There's no threads. There's no ability to pause. There's no sleep call. There's no explicit shared memory, so you can't have multiple threads talking to shared memory and so on. And the API call order is also quite important. So you can't call, or if you call certain APIs, you are forbidden from calling, forbidden from making other calls afterwards. Okay. So it's just one of the features of their system. And so we started to just mess around a little bit, and we were looking for some examples of how to provide those missing building blocks, because many of those things are building blocks. And so here's something really silly. They provide, or you are limited to 200,000 statements, but an expression can be, I think, almost 32K long. So you can make an almost arbitrarily long expression, which only counts as a single statement in the code. And so what we're trying to do was to fudge out a sleep call. And so here we've just got a whole bunch of cube roots chained together that take a lot of time on the processor, but only count as a single statement that's been executed. And so we can sort of start to build up a sleep call. We can also do something similar with synchronization. So if we're trying to get a lock, if you've got multiple invocations of Apex all trying to access a given resource or do one thing, or we're trying to have a first past the gate kind of scenario, you can fudge out a lock using, so they do support locks in the database, and using that as a building block, you can kind of get locks in your code. Shared memory you get if you consider the database as shared memory. Triggers they support in terms of the database itself. Threads we gave up on. Okay, so with all of this, one of our focuses on Salesforce.com was trying to bypass this governor. So that's the thing that protects people in the multi-tenant environment from each other. Okay, well, let's go after the thing that's protecting people. But there are a number of ways to approach this problem. And the way that we chose to approach the problem was pretty much through what we called event loops. So based on a single user interaction, the attacker, we wanted a whole chain of execution to continue on the Salesforce side. In other words, we wanted to get continuous execution going without having to involve a third party at all. And so there are a couple of ways that you may immediately think of. The one is to have a web page that calls itself through a web service call. So you have a web page that is called in response to a web service call, but within that web service call, it calls itself. And you can try to get a cyclical invocation going. But that doesn't work because they have checks specifically for that. So we wanted to steer clear of third-party interference, so we did settle on email. And pretty much what the process that we settled on was this. For an external party sends an email to a predefined address. This kicks off some Apex in which we can do whatever stuff that we want to do on this round of execution. That round of execution is obviously limited by its set of governor limits. But as soon as it's done, we insert an object into the data store which kicks off a trigger, which sends an email back to our original email address. And so the cycle continues. And what it means is that every time we go once around the cycle, we get another set of governor limits. So we can scale those governor limits by the number of times we can get that email or get that cycle going. And so what eventually we bumped into is a hidden quota on the number of received emails in this case. But you get up to 1,500 rounds of execution, which depending on your job may or may not be sufficient. But of course, whatever that job is up to the user's imagination. And so we put kind of these building blocks together. We looked around and we thought, well, what's a reasonable demo for a hackathon? And the example that we chose to go with was Nikto, which you probably, or you may or may not be familiar with it. But we call this thing Sifter for the Salesforce Nikto. And pretty much we just ported Nikto into the cloud. And it's exactly as you would expect, that we have a list of URLs that get scanned on a target website, and that we pull out when the response matches given values. And so we kick off this event loop, and in every iteration of the event loop, we take a subset of the test that we want to conduct against the target. We do that, store the data, move through the next cycle. The question is, why do you want to do this? Well, for one, there's an element of, well, because we can. But it's free. So if resources are tight for you, and you've got a Salesforce.com dev account, well, then it's free, which is quite cool. In South Africa, it may count as fast, depending on where you are sitting. We don't have loads of international bandwidth, and the little that we do have is quite expensive. So to be able to offshore your bandwidth cost is quite a nice thing. And it gives you a degree of anonymity. So now you're scanning from Salesforce's servers, not from anyone else's servers. Okay. But mostly it's just a proof of concept kind of thing. So allow me to run this video. Okay, so I'll just talk through, there's 7 parts in here. So we log in, I'm just going to show you a little bit about the config. This is the interface to Salesforce. So you write your Apex within their website. This is just an example, or this is just a listing of the Apex classes that we needed. So there were a couple of things. There's also other testing classes in there. We also needed custom objects in their database, as well as the trigger that would get set off when we inserted stuff into the database. And that trigger would be sending the email back to ourselves. Okay. This is now the code that actually runs when an email is received. So that's the email address to which we need to send our looped email. Now, the one thing that, if you are familiar with Salesforce.com, you'll know that, as I said before, you need to send, or you need to explicitly allow outgoing connections to websites. And you can't do that except through the web interface. There's no API to add support to do that. So here, I'm showing that the allowed endpoints does not contain the site that we're going to scan. Just because at the end, I'm going to come back and show you that it's been added, which we do programmatically through abusing their web interface. So on this side, we've got the attacker console. And so our only interaction with this service is going to be via email, which makes it also quite cute, because email can be really anonymous. If you choose to use Hushmail or whatever, this thing becomes quite hard to track. So once you've set up the initial system within Force.com, the attacker gets to conduct everything, all of his commands and all of that via email. And so we've got a little shell script that's a wrapper here. We're going to be looking at the attacker's console, and we're also going to be looking at the victim's Apache log to see the scan as it comes through. Okay, so that's just the shell script that sends an email and so on. And we're going to start tailing the logs. So we specify the site that we want to attack, and we say start the scan, and we start watching the logs. And this is real-time waiting now as the scan comes through. And it's not incredibly fast, but as I say, compare that to South African bandwidth. What you do see, though, is that the notification mails as each iteration of the loop completes are starting to come through. While that scan continues, here I'm just showing you that the endpoint was indeed added successfully to the web interface, to the force.com configuration without having to use the web interface. So there, endian.cosa has been added programmatically. So the scanning continues, and shortly it shall be completing. And so I've spoken about we get notification mails as each loop of that or as each cycle of that event loop continues. Here the scan ends, and then the final result is shown in the emails that we receive. So those are the results of each individual cycle, and then on the last one we get the overall results. Now, what's interesting about this is just from a timing perspective, you get timing within a granularity of a minute. So you can see scan starts at 1:05, it ends at 1:16. So in 11 minutes we get to scan sort of a host on the internet. Okay. And so this is an example. And so it's an example of how to abuse the services that are available in the cloud. So is it a vulnerability within force.com? Well, debatable, probably not. We're just taking their supported services to the edge of where they should be going, which is developing attack tools. And we're finding tricks to get around their more obvious limitations. So they don't allow continuous execution. Cool. Let's see if we can cycle execution to give us the illusion of continuous execution. So it could be fast or faster with a little more bandwidth. It's free. And depending on how you structure it, you may be able to leverage this into denial of service. But we certainly didn't go anywhere close to that. You also got to ask about, is it possible to DOS Salesforce.com through having such things? Again, that's not a question that we were particularly keen to answer, given all of the issues with testing cloud providers. Of course, there are many cons to this. Prone to monitoring is a big one. It's custom language and platform. And this particular technique is governed by email limits. So we said that's cool, but the problem is each account we've only got 1,500 sort of loops a day for the account. Can we improve on this? Well, actually we can. In this case, accounts are zero cost. They cost us nothing. We're a developer account. They're free. We just need to sign up for them. So instead of trying to go really deep with what you can do with one account, you can scale it breadthways. Get lots and lots of accounts and see if you can start up many instances of a given piece of code that runs for 10 minutes and see if you can start to affect the load on one machine or on their clusters. And this is useful because accounts can communicate through things like web service calls or through email or whatever. And so all that's stopping us at this point is the ability to auto-register, because we don't actually want to have to register 1,000 accounts by hand. And so we have a look at their page to see if we can auto-register. What you see is that actually it sucks. They've got a captcha. And so strength of captcha aside, we didn't particularly feel like breaking the captcha. So we kind of looked around and we're doing hacking and security and stuff, and we're looking for the easiest way to do something. And so that image is generated by a PHP script. So we just curled the PHP script. And actually it was funny. Clearly someone had left debug information in the PHP script. And so right at the end, someone has run print R on the structure that is containing the contents for this image. And actually you can see that they've got the text of the image embedded right at the bottom of the image itself, which was a little bit funny. And so with that, it was possible, obviously, to automate registration. Got to give Salesforce.com shouts, though. When we reported this, 15 minutes later, they fixed it. So they're on the ball. They're quite proactive. The thing, though, there we go. So what are some of the future directions for this particular approach? Sifter is really, it's a basic POC. There's nothing magic about it. But there's a lot of possibilities given that this language is Turing complete, and there are all of these resources that are backing it, and there are some interesting APIs. And so there are a few improvements to the language. So if we talk about insidious and expansion or an expanding of features, when we tested Salesforce last year, in the middle of the year, they were at version 15 of their language, and at the moment they're on version 19. So every 3 months there's a revision and features get added. So it's definitely growing. There's some other stuff there. But I want to carry on and talk Amazon Web Services, which is sort of, I guess, the meaty part of this presentation. And it's cool. It really is that cool. They've got a whole bunch. So when you hear of Amazon Web Services, AWS, there are many services that are structured underneath that. And in fact, this is not even the full set. And so the things that we looked at and the things that we touched in our testing were EC2, S3, SQS, and DevPay. And broadly speaking, EC2 gives you the ability to run virtual machines. S3 gives you the ability to store data at Amazon. SQS gives you a queue service with messages, so you can have communications between virtual machines. And DevPay is a way for people to sell images that they do create. But there's many other. Well, there's a bunch of other services that they have that we ignore, okay, so we don't touch at all in this presentation. If we talk briefly about EC2 and how it works, I mentioned at the start of the presentation that it's an example of infrastructure as a service, and it is where Amazon provides you with the ability to create and run virtual machines, so your own virtual machines. And it runs in their data centers, so they're responsible for everything underneath from the hypervisor downwards. Okay, that's all of their issue. But everything on top of the hypervisor is what you are responsible. So it gives you, in essence, root access to a Linux box at the click of a button. And you're the only one with access to that machine. The costs are scalable because it's elastic and all of this really, really cool stuff. So the way that you go about, well, one of the videos demonstrates how you can actually go about creating an image. The next one is S3, and S3 is the storage service. Excuse me. And where AWS provides you with the ability to compute and to run processes, S3 is actually where your data gets stored. So for a long time, in fact, I believe Amazon, or certainly for a long time, Amazon did not allow persistent images. So once your image died, whatever was on it or running disappeared. If you wanted to store that data from image to image, you needed to store it in S3. So AMIs were not persistent at all. So S3 is the way that you can store the stuff. And again, it's all of that good cloud stuff, as one would expect. There's a cute little Firefox add-on that allows you to treat your S3 bucket as just another point on your desktop to store stuff, so you can just move files over and so on. And it's kind of cute. And so broadly speaking, what they give you is this. S3 allows you to create buckets, and you can name the buckets, and within that you just drop objects, just blobs of data. So there's no... this isn't a file system at all. There's none of those primitives that we expect in the file system. There's no permissions or locking or any of that stuff. It's just you create a bucket that only you have access to, and within that bucket you can drop data. And so this is an example. You may name your bucket McCulver images, and within that you just drop images, or you may name it public.blueorigin.com, and within that drop both HTML and images, whatever. You just get to label the bucket, and you get to drop in and label blobs of data. Then SQS is a little bit, or SQS is the way that elasticity is provided. So it's just a queuing service that your images can make use of, and so the typical producer-consumer paradigm applies. You may have one or two images producing a whole bunch of data that needs to be processed. They drop it on the queue, and on the other side you've got images that are pulling data off that queue. But you can also tie elasticity to the queue and so on. So when the queue grows, you scale and so on. The SQS is just a useful means for communicating between images. And so we looked for a similar thing that we had with Salesforce.com in terms of trying to steal processing time, trying to get more execution than we should have. And so we wanted to see if we could get that, steal some of that from Amazon, from Amazon's users. So we started to look into this. Now it's interesting. You'll see there that this is a list of all the AMIs that, and AMI is an Amazon machine instance. So it's just it's a virtual machine. So it's one virtual machine. And this is a list of all the AMIs that they have. What's interesting is you'll see there's 2,768 AMIs listed. Of the nearly 2,800 images, Amazon themselves provide 47, which is a really small percentage. So Amazon is not the source for most of the images on EC2, which means you got to ask the question, well, where do they come from? They come from people in the community. You can create an image and stick it up on Amazon and have it appear in this list that everyone else gets to see. One of the promises of the cloud is that these guys are pros at what they do. They do it really well. But if your image that you're running is built by a guy in his spare time, that promise is a bit of a false promise. So what we decided to do was, let's try and measure the security of all of these images for some definition of measure. And so we wanted to find out, well, of all of these AMIs, how many of them are vulnerable to common things? But you can't really scan from outside because it gets detected, blah, blah, blah. So what we tried to do was the following, and you also can't scan other people's images. So that'll get you kind of booted. So from within our own account on EC2, we get a list of all the available images. We put these on a queue, so the SQS. We then boot up 20 virtual machines, of our own virtual machines. And each of these runs Nessus. Okay, so it's got a Nessus instance. And each of those virtual machines boots up, or pulls from the queue an image that needs to be tested. It boots up that image that needs to be tested. It scans the image. Once the scan is complete, it shuts that image down. Okay, so we parallelize Nessus scanning of the AMIs that Amazon provides. And once the scans are completed, we store the data in S3, and then the attacker gets to look at that data. And it's really interesting. So, 2,800 images, there's almost 1,300 issues that Nessus rates as high. Okay, so that's almost 1 in 2 images has got some kind of high vulnerability. And almost 1 in, what did we say there? Almost 1 in 5, very roughly speaking. Images has got a critical vulnerability. Now, it's not necessarily completely accurate. I'm guessing a bunch of those are much more vulnerable than others. But it is a bit scary that of all of these images that are out there, 646 critical vulnerabilities. And that's Nessus. I mean, we're not talking about, we're not talking 0-day here. We're talking well-known issues that Amazon puts out. Some of the other things that we found. So starting to dig through the images, looking through bash history, looking through MySQL history, looking through all of these things. Pull out passwords. You manage to pull out keys that people use to create images. Manage to pull out people's GPG keys and so on. And these are all things that were left in the image when the creator built the image and uploaded it to Amazon and left it there. Okay. So this data doesn't belong to Amazon. It belongs to the people who originally created the image. But we wanted to go again for all the little attacks that people don't seem to have pondered too much. So license stealing is kind of funny just because it was so successful. So we take an image off. So Amazon themselves provide a bunch of Windows images. Boot one of the Windows images, so you use the gloriously named Magical Jelly Bean key finder. You run that. You get a license key from that, and so that's the license key that Amazon used to install. Then on our own machines, we install a VM in which we run in Windows 2003 server. And that license key works. So here it is. We've got Microsoft Windows Server 2003 Data Center Edition running based on the license key we pulled from Amazon. So in other words, you pay to boot one EC2 instance, and now you've got a license key worth whatever. And just for good measure, we wanted to ensure that this thing would verify with genuine software advantage stuff. So the genuine advantage stuff. And this is just an example of we're pulling updates. In other words, genuine advantage has verified that this is indeed a legitimate install of Windows. Okay, so that's just something that doesn't seem to have been considered too much. I mean, if you're putting software out there, you've got to consider how it's going to be built and licensed and all of that. Amazon DevPay is one of the other services, and it's quite interesting because it allows you to create your own image and upload it to Amazon and have other people use that image, and you get paid. So you kind of do a revenue sharing with Amazon, which is quite cool. And so it takes us to our next video, in which